I feel like there are a few phrases in the English language that just instantly trigger a physiological response, like a cold sweat, elevated heart rate.
Oh, absolutely. Like, we need to talk.
Yeah, exactly. Or maybe I think we took a wrong turn in this neighborhood.
Hmm.
But if you write software for a living, especially if you're the guy stuck fixing things on a Friday night, there's one specific sequence of 5 words that is just absolutely guaranteed to spike your blood pressure.
I know exactly where you're going with this. It's the Universal Developers Get Out of Jail Free card, and probably the absolute bane of any project manager's existence.
It works on my machine.
Yep, there it is.
I mean, we have all been there. You spend months building this gorgeous, highly complex application on your local laptop. It's just, a masterpiece of modern engineering.
It hums perfectly.
Exactly. The UI is snappy, the database queries are lightning fast, and you've finally reached the finish line. You hit deploy, you push the code to a live production server, and instantly, bam.
Total catastrophic failure.
Right. The application crashes, the users are furious, your boss is glaring at you across the room, and all you can do is hold up your hands and just utter those fateful words, "Hey man, it works on my machine."
Which, to be fair to the developer, is usually technically true,
True. Yeah.
but it's also entirely useless in the context of, like, actually delivering a product to real users.
Right. And that shared trauma is exactly why we're plunging into this topic today. So welcome to the deep dive, everyone. Our mission today is to thoroughly demystify the dark, often pretty intimidating art of software deployment.
And it really is an art form, honestly.
It is. So whether you're a seasoned developer who's just, utterly exhausted by manual, fragile deployment processes, or maybe you're a curious learner trying to figure out what that corporate buzzword DevOps actually means when the rubber meets the road, this discussion is going to give you the exact blueprint.
Yeah, we're unpacking a massive, incredibly comprehensive masterclass today. It's from freecodecamp.org, taught by instructor Gavin Lawn.
And the goal here is taking a full stack application, containerizing it, and building a professional continuous integration and continuous deployment pipeline, a CI/CD pipeline.
Right, and we are deliberately avoiding, like, abstract theory here. The source material anchors this entire sprawling discussion around a very specific, highly complex test subject.
Yeah, it's a project called Magic Stream.
Exactly.
And Magic Stream is essentially a bespoke movie streaming service.
Yeah.
And the architecture is what makes it, I think, the perfect candidate for this deep dive. Because it's not just a simple static HTML web page, right?
Not at all.
It's got a React front end handling the user interface. It has a Golang web API running the backend logic. It utilizes a MongoDB database to store all the persistent user data.
And just to ensure it represents the absolute cutting edge of modern web development, it has an OpenAI-powered recommendation engine baked directly into that backend.
Right. Deploying a simple blog is trivial. But deploying a multi-tier distributed application with a separate client, a compiled server, a NoSQL database, and external third-party AI integrations.
Yeah, that is historically where the wheels completely fall off the wagon.
Seriously.
That level of complexity is the exact breeding ground for the works on my machine phenomenon.
Okay, so if you want to understand how to take your fragile code from a messy local folder on your laptop to a highly resilient, fully automated cloud server where you literally just type git push and the entire internet updates, you are in the right place.
It's a game changer.
So let's unpack the root cause first.
Mm-hmm.
Before we start building automated pipelines, we really have to isolate the disease. Why is deployment traditionally such a nightmare?
Well, it really boils down to a fundamental concept, which is environmental drift.
Okay, drift.
Yeah. When you're writing code on your personal laptop, your development environment, you have a highly specific, very idiosyncratic setup. You're running a specific operating system, maybe Mac OS Sonoma or, Windows 11.
Right.
You have very specific versions of programming language runtimes installed globally on your machine. You've got specific background services running, user permissions, network configurations, and all these specific environment variables injected into your terminal profile.
And the source material is very explicit about Magic Stream's requirements too. Like the React client requires Node.js version 20 to build properly.
Yes.
And the Go backend specifically requires Go version 1.24.2.
Right. So now consider the traditional deployment model. You take the raw code files you wrote in that pristine, perfectly tuned local environment, and you just drag them over to a bare metal production server.
Which in the case of the source material is a Hostinger virtual private server running a generic Ubuntu Linux distribution.
Exactly. So what happens if that Ubuntu server was provisioned, say, 6 months ago and is running Node version 16?
Well, the React app is just going to fail to build, right? They'll likely throw a whole cascade of syntax errors because Node 17 doesn't support the newer JavaScript features that Node 20 does.
Spot on. And what if the server has an outdated Go compiler? The binary won't compile, or it'll just panic at runtime.
Ugh, the worst.
Or what if the file system permissions on Linux prevent your application from writing logs to the directory it expects, just because the path structure is fundamentally different from your Windows C drive?
Right, the application just crashes.
Mm-hmm.
So without a mechanism to strictly standardize the host environment, the deployment server has to have every single dependency, every runtime version, and every configuration manually installed and perfectly maintained to match your laptop.
Which introduces a massive, unpredictable set of variables.
So the historical solution to this was virtual machines, right?
Mm-hmm.
Like you would just virtualize an entire operating system, bundle your app inside it, and ship the whole heavy operating system to the cloud.
Right, VMs.
But that seems incredibly bloated, doesn't it? Like, if I just want to run a TinyGo web server, shipping an entire 20-gigabyte Windows virtual machine with a graphical desktop and a kernel just to run a 5-megabyte app, I mean, that's overkill.
Oh, it's massive overkill. Virtual machines solve the isolation problem, sure, but at a huge cost to efficiency. Because every VM requires its own full operating system, its own kernel. You're allocating gigabytes of RAM and CPU cycles just to keep the OS alive before the application even starts doing anything.
Right.
This is exactly why the industry shifted to the solution at the core of this course, which is containerization, and specifically Docker.
Okay, let's make sure the terminology is absolutely crystal clear here, because I hear developers use Docker image and Docker container interchangeably all the time, and the source material is adamant that they are very distinct concepts.
Yes, very distinct.
I'm visualizing this kind of like an industrial manufacturing process.
Mm.
So the Docker image is the master mold at a toy factory. It's the declarative physical blueprint.
I like that.
And the Docker container is the actual tangible plastic action figure that pops out of the mold and goes onto the shelf.
That is a highly accurate mental model, actually. The Docker image is a static, immutable, read-only file. It contains the exact operating system instructions, the precise language runtimes like that Node 20 and Go 1.24.2. We mentioned the required system libraries and your application code.
It's the recipe.
Exactly, it's the recipe. Crucially, an image does not execute. It occupies disk space, but it uses 0 CPU and 0 RAM.
So it just sits on the hard drive holding the instructions.
Right. But when you issue a command to the Docker daemon to run that image, the engine allocates memory, creates an isolated process space, and instantiates a Docker container. The container is the living, breathing, in-memory execution of that image.
Got it.
So returning to your manufacturing analogy, you invest the time to engineer one perfect master, mold the image, and from that single mold, you can stamp out thousands of perfectly identical functioning action figures, the containers.
And because that container has its own heavily isolated, perfectly packaged internal environment, it is completely agnostic to the host server. I mean, it doesn't care if the hosting your VPS is running Ubuntu or Debian or Red Hat. Nope.
Doesn't care at all.
It doesn't even care if the host server has Node.js installed at all, right? Because the container brings its own pristine copy of Node 20 tucked inside its walls.
Exactly. By moving the environment inside the deployment artifact, you entirely eliminate the variables of environmental drift.
Wow.
If the container executes successfully on your macOS laptop, the mathematical architecture of Docker guarantees it will execute with the exact same behavior on a Linux production server. The environment is completely portable.
This highlights a cultural shift that the instructor emphasizes pretty early on, actually. DevOps, the philosophy and practice of bridging software development with IT operations, it's a distinct discipline from writing the application code itself.
Right.
Like a developer doesn't necessarily need to know how to write a Docker file to write good Go code.
No, they don't. And in massive enterprise organizations, you often find strict silos. You know, an entire engineering team dedicated solely to writing features, and a completely separate platform engineering team dedicated to DevOps, infrastructure, and deployment pipelines.
So the developers write the code, throw it over the proverbial wall, and the DevOps guys figure out how to containerize and scale it.
Precisely.
But the course makes a very compelling argument against that siloed approach, though. It argues that a developer who understands DevOps, who can write their own containerization scripts, fundamentally changes their value proposition in the job market.
Because you cease to be a liability at the end of the sprint cycle.
Exactly.
A developer who comprehends how their code interacts with the underlying infrastructure, who understands network ports and container life cycles, is a developer who can independently troubleshoot their own production bugs. They aren't just writing logical functions anymore, they are engineering deliverable software.
Okay, so that sets our foundation.
Mhm.
We need to containerize Magic Stream to ensure it survives the journey to the cloud. But the source material takes a very interesting pedagogical detour before we actually start writing raw Docker code in the terminal. It deliberately shows us the path of least resistance first,
Right.
the GUI abstraction.
Yeah, cloud providers are highly incentivized to make deployment as frictionless as possible to attract developers, right? The easier it is, the more likely you are to use their service.
Makes total business sense.
So the course demonstrates this by utilizing Hostinger's built-in Docker Manager facility, which is a graphical user interface provided alongside their virtual private server plans.
The speed of this demonstration is staggering, honestly.
Oh.
You authenticate into the Hostinger web dashboard. You don't open a secure shell. You don't type a single Linux command.
Yep.
You navigate to the Docker Manager visual interface, and you literally just click a button labeled Compose from URL. You paste in the raw URL pointing to a Docker compose.ml file hosted on GitHub, and you click Execute.
It's that simple.
And the platform parses the file, automatically downloads the required Docker images from the internet, provisions the internal network, and boots the entire multi-tier application. It feels like a magic trick.
It really is the pinnacle of infrastructure abstraction. The platform hides all that heavy lifting of image pulling, container lifecycle management, and network bridging behind the sleek, user-friendly interface.
Yeah.
But, however, the instructor carefully points out the limitation of this magic. There is one critical configuration step that the system cannot automate for you.
The environment variables.
Bingo.
Even with the automated GUI, the developer has to manually input a series of key value pairs into a visual table.
Mm-hmm.
Let's dig into the why here. Why do environment variables even exist? If the developer needs an OpenAI API key to make the movie recommendation engine work, why not just type the text string of the API key directly into the Go source code, save the file, and push it to GitHub?
Well, doing so would violate one of the most foundational principles of software security and the 12-factor app methodology.
Okay, 12-factor app. What does that mean in this context?
Basically, you must maintain strict separation between your application's logic, the code, and its configuration. Sensitive credentials, things like API keys, database connection strings, and cryptographic secrets, they must never be hard-coded into the source code.
Because if you commit an OpenAI API key to a public or even a private Git repository, it becomes a permanent part of the version history.
Exactly. And malicious bots are constantly scraping GitHub for exposed keys. I mean, within seconds of pushing that code, a bad actor could scrape your key and rack up a massive, potentially bankrupting bill on your OpenAI account.
Yikes. So the code itself acts purely as a structural template. The Go backend is programmed to basically say, hey, when I boot up, I am going to search the surrounding operating environment for a variable named OpenAI API key. Whatever text string I find there, I will use to authorize my requests.
That's it exactly. The sensitive values are injected dynamically at runtime. So when the Hostinger Docker Manager initializes the container, it passes those secret values into the container's isolated environment.
The source outlines the specific variables required for Magic Stream. We've got secret key and refresh token secret key, which handle the cryptographic signing of JSON web tokens for secure user login sessions.
Yep.
We have the aforementioned OpenAI API key. And then we have variables dictating the network architecture, like epiHostIP. You have to set this to the actual public IP address of the Hostinger VPS so the React client knows the precise internet address to send its data requests to.
Right.
But there's one variable that caught my eye because it addresses just a universal headache in web development, the allo origins variable.
Ah, yes. The configuration to handle cross-origin resource sharing. Or, as everyone knows and loves it, CORS.
I feel like every front-end developer out there has stared at a bright red CORS error in their browser console and just wanted to throw their computer out the window.
It's a rite of passage.
It really is. I know it's a security feature, but let's break down the exact mechanism of why CORS exists and how this environment variable solves it.
So, to understand CORS, you really have to understand the same origin policy, which is a fundamental security model enforced by all modern web browsers.
Okay, same origin policy.
Right. Imagine a user logs into their bank account at bank.com. The browser stores an authentication cookie. Now, if that user then opens a new tab and visits a malicious website, let's call it evil-hacker.com.
Creative name.
The malicious site's JavaScript might try to silently send a request to bank.com to transfer funds. Because the browser automatically attaches the authentication cookie to requests going to bank.com, the bank might actually process the malicious transfer.
Ah, okay. So the browser acts as a bouncer. It says, wait a minute, the code making the request came from evil-hacker.com, but it's trying to access data on bank.com. Those are two totally different origins. I'm going to block this request to protect the user.
Precisely. The browser restricts cross-origin HTTP requests initiated from scripts. However, in modern decoupled web architecture, like what we have with MagicStream, we want cross-origin communication.
Because we have a React front end running on one domain or one specific port and a Go API running on a completely different domain or port.
Right. So when the React app tries to fetch the movie list, the browser intercepts it and initiates a pre-flight request.
Pre-flight request, okay.
It basically sends an HTTP options request to the Go server, essentially asking, hey, are you willing to accept a data request from this specific client origin?
And if the Go server isn't explicitly configured to say, yes, I trust this origin, the browser instantly kills the request.
Yep.
And you get the giant red error.
If you get the red error.
So that environment variable, allow origins, is dynamically passing a list of trusted URLs to the Go server. So when the server boots up, it reads that variable, configures its internal router, and now when the browser sends that pre-flight request, the server responds, yes, I recognize this front-end domain. Let the data through.
Exactly. It is a perfect example of why environment variables are essential for more than just secrets. I mean, they allow you to fundamentally alter the behavior and security posture of the compiled application without touching a single line of code.
Okay, so the hosting your GUI provides this incredibly slick visual way to deploy the YAML file and inject those environment variables. And it works flawlessly in the demonstration.
It does.
But this triggers a pretty significant question. If the graphical interface is this powerful and it abstracts all the pain away with one click,
Yeah.
why does the course pivot?
Why do we spend the rest of the time learning the hard way, right?
Yeah. Why do we spend the remainder of the material learning the archaic manual terminal commands? Like, what is the danger of relying entirely on the magic button?
Well, the danger lies in the concept of leaky abstraction.
Leaky abstraction.
Yeah. A graphical interface is a rigid, predefined set of rules created by a platform provider. And it works perfectly as long as your application strictly adheres to those predefined rules. But software engineering is inherently chaotic. When a deployment inevitably fails, when a container enters a crash loop, when network latency spikes, when you need a custom build step that the GUI just doesn't offer a button for the abstraction breaks down.
So if you only know how to click the button and the button stops working, you have absolutely zero diagnostic capability.
You're completely stuck. Furthermore, graphical interfaces are fundamentally incompatible with true CI/CD automation. If the ultimate goal is that a simple code commit automatically triggers a deployment to the live server, you can't rely on a human logging into a web portal to click a button.
Right, that defeats the whole purpose of automation.
Exactly. You must understand the underlying scriptable terminal commands to orchestrate that automation.
Which transitions us deep into the technical weeds.
Ah.
We have to understand how those master moles are actually manufactured from raw materials. We're opening our code editor and writing Docker files from scratch.
Yes, we are.
Let's analyze the syntax and the strategy behind these files.
So a Docker file is essentially a declarative text document. It contains a sequential linear list of commands that the Docker engine executes to assemble an image layer by layer.
Layer by layer, got it.
And the source material outlines two distinct files, one for the Go API server and one for the React client.
Let's focus on the backend file first. The very first line dictates the foundation. It says, from golang.1.24.2 Alpine. Now, I noticed the specific use of Alpine here, and it seems to be a recurring theme in modern containerization. Why not just start from Ubuntu or a standard Linux distribution?
Well, it really comes down to surface area and efficiency. A standard Ubuntu base image might be, hundreds of megabytes in size. It includes a vast array of system utilities, package managers, and libraries designed to support a full desktop or server operating system.
Right.
But when you're deploying a Go binary, which is already compiled into a self-contained executable, you just don't need 99% of those utilities.
So all that extra bloat just means the image takes longer to build, it consumes more bandwidth to upload to a registry, And takes longer for the production server to download.
Exactly. And additionally, and perhaps more importantly, unused software packages are a massive security liability.
Oh, because every utility included in the container is a potential vector for a vulnerability.
Right. Alpine Linux is an ultra-minimalist distribution. It's built around Muscle Libidic and BusyBox. A base Alpine image is often under 5 megabytes.
Wow, 5 megabytes. That's
Yeah,
small.
it provides the absolute bare minimum required to execute a process, resulting in vastly smaller, faster, and much more secure containers.
So we lay down our 5 megabyte Alpine foundation. Next, the Docker file uses the copy-y command to move the go.mod and go.sum files, which track the project dependencies into the container.
Yep.
It runs gomod download to fetch those third-party libraries from the internet. Then it copies the actual application source code in and uses the expose command to document that the application will listen on port 8080.
Right, and the React client's Docker file follows a nearly identical logical flow, just substituting Node Package Manager commands instead of Go commands.
Okay, but writing the blueprint is only half the battle. You have to actually feed it to the factory.
To execute the blueprint, you utilize the Docker Command Line Interface, or CLI. The specific command demonstrated is docker build -t magicstream-appy.1.1.000.
Let's treat the command line interface like the grammar of a sentence because I think it helps clarify exactly what is happening here.
Go for it.
Okay, so the subject of the sentence is Docker, telling the computer which program to run. The verb is build, the specific action we want the program to take. We modify the verb with an adjective, the -t flag, which allows us to tag the resulting image with a human-readable name and version number, magicstream-appy.1.0.0.
Perfect.
But the object of the sentence, the absolute most critical part of this command, is that tiny period sitting all by itself at the very end. The dot. The instructor emphasizes it heavily. What is the dot doing?
That period specifies the build context.
Okay, what does build context actually mean mechanically?
Right, so the Docker architecture utilizes a client-server model. When you type commands into your terminal, you are interacting with the Docker client. The actual heavy lifting of building the image is performed by the Docker daemon, which is a background service running on your machine.
So they're two separate things.
Yes. When you initiate a build, the daemon needs access to your local files, your Go code, your React components to copy them into the image. The build context tells the client exactly which directory of files to package up and send to the daemon. And the dot is just a Unix shorthand for the current directory you are sitting in.
So if you omit the dot, the command fails entirely because the daemon is essentially saying, hey, you gave me the recipe, but you didn't tell me where the kitchen is. I have no ingredients.
That's a great way to put it, yeah.
So the build succeeds. We have our image. We can manually execute it with a Docker run command, passing in our .env file containing the secrets, and the application springs to life.
It does it.
But the source material exposes a massive architectural conflict right here. A conflict between the philosophy of Docker and the default behavior of modern front-end tooling, the Vite quirk.
Ah, yes. The Vite quirk. This specific section of the material is brilliant because it addresses a severe gotcha that catches, honestly, almost every junior developer transitioning from local development to containerized production.
Let me set the stage for this one. The React front-end for Magic Stream is scaffolded using a build tool called Vite. And Vite is currently the industry darling, right?
Yeah, it's everywhere.
It's incredibly fast, highly optimized, but the way Vite processes code before deployment fundamentally breaks the portability promise of Docker.
It does.
So we need to unpack the mechanics of a front-end build process. Browsers don't actually understand the complex modular React code we write, do they?
No, web browsers natively execute standard HTML, CSS, and plain JavaScript.
Yeah.
When you write a React application, you're utilizing modern ECMAScript features, JSX syntax, and all these complex module imports. To make this code run in a browser, a tool like Vite must perform a series of complex transformations.
Yeah.
It transpiles the modern syntax into older, widely compatible JavaScript. It minifies the code, stripping out white space and renaming variables to reduce the file size for faster network delivery, and it bundles hundreds of individual files into a few highly optimized static assets.
Static assets, meaning once Vite finishes its job, the resulting files are just raw text. They don't compute anything on the server just takes those text files and hands them directly to the user's browser.
Exactly. Now, recall our discussion about environment variables. The React code requires the API URL to know where to send requests to the Go backend.
Right. It needs to know where the server is.
During local development, the Vite server dynamically reads your .env file and provides those variables to your code. But when you execute the production build command, Vite encounters a structural problem. Because the final output is purely static, it cannot read a .env file at runtime on the server. The files are dead.
So what does Vite do to solve that?
Well, by default, Vite performs a process called static replacement.
Static replacement?
Yeah, during the build compilation, it reads the environment variable. Let's say API URL is set to localhost on your machine, and it literally searches through the JavaScript syntax tree, finds every reference to that variable, and hard codes the string localhost directly into the final minified static files.
Oh, wow. So the variable is permanently baked in.
The variable is permanently baked in.
And right there is the catastrophic failure for containerization.
Yep.
Because the central tenet of Docker is immutability. You build a single image once, and you deploy that exact same image to staging, to testing, and to production, merely altering its behavior by injecting different environment variables at runtime.
Exactly. But if you build the React Docker image using Vite's default static replacement, the URL is permanently baked into the static assets as localhost. So if you push that image to the Hostinger production server and attempt to inject the live public IP address via the Hostinger GUI, it accomplishes absolutely nothing. The environment variable is injected into the container, sure, but the static files inside don't care. They still say localhost.
The front end running on the internet will try to contact a Go server running on the user's local laptop. That's hilarious, but also terrifying.
It's a huge problem.
So to fix it using standard Vite behavior, you would have to completely recompile the source code and rebuild a brand new Docker image directly on the production server using a production-specific .env file.
Which means you lose the entire benefit of shipping a tested, immutable artifact.
Right. So how does the instructor engineer a bypass? How do we intercept static files and inject dynamic data at runtime?
The instructor implements a highly sophisticated workaround utilizing a bit of architectural sleight of hand and a classic Linux utility.
Ooh, I love a good hack.
It's a great one. Instead of allowing Vite to process the environment variables during the build phase, the developer creates a brand new file in the public directory called nv.template.js.
Okay, a template file, not actual executing code.
Correct. Inside this template, they write a tiny script that assigns a global variable directly to the browser's window object. It looks something like window.env-AERL.
Notice the syntax there. The value isn't a real URL. It's a string containing a $sign. API URL. It acts as a deliberate placeholder.
Exactly. Then they refactor the actual React source code. Instead of utilizing Vite's environment variable system, the React components are programmed to read the URL directly from that window.env object.
So Vite builds a code, sees no reference to its own environment variables, and just leaves the code alone.
Right.
The static files are generated, and they are completely agnostic to the environment. The image is portable again?
Portable again?
Lied. The placeholder is still just a string with a $sign. When the container actually boots up on the server, how does that placeholder get swapped out for the real hosting your IP address?
This is where we leverage a powerful Unix command line utility called nsubst, short for environment substitution.
Ah, msubst.
Yes. In the Docker file, the command to start the container is modified. Before the web server is allowed to serve the files, a brief shell script executes. This script feeds the nv.template.js file into the nsubs program.
Okay.
The utility scans the text of the file. Whenever it detects a variable pattern matching an environment variable that was injected into the container at startup, it dynamically rips out the placeholder and pastes in the actual runtime value.
It essentially rewrites the file on the fly.
It creates a new finalized nv.js file containing the real production URL and saves it in the directory. Then the web server starts and delivers that freshly minted file to the user's browser.
Man, that is an incredibly elegant hack. I mean, it bypasses the build tool's static compilation entirely, intercepts the delivery at the very last millisecond, dynamically populates the configuration, and preserves the absolute portability of the Docker image.
It really is elegant, and it is a perfect illustration of why relying solely on a graphical interface is dangerous. If you didn't understand the underlying mechanics of static bundling versus runtime execution, you would spend weeks trying to figure out why your API requests were failing in production.
You'd just be staring at localhost errors forever.
Yeah,
It really bridges the gap between software development and systems engineering.
completely.
So we have successfully engineered individual portable containers. But Magic Stream requires a React container, a Go API container, and a MongoDB database container. Running these manually is excruciating. I mean, if I have to open 3 separate terminal windows, type out Docker run with 10 different flags for ports and variables for each one every single time I want to boot my app, it is entirely unscalable.
Yeah, you go crazy.
We need orchestration.
Yes. Managing the lifecycle and networking of multiple interdependent containers manually is highly error-prone. For a single host environment, whether that is your local laptop or a single Hostinger VPS, the industry-standard orchestration tool is Docker Compose.
So we return to the docker-compose.iml file. This is the exact file we pasted into the Hostinger GI earlier, but now we actually get to see the matrix. We're looking at the raw code. I noticed it uses YAML. What exactly is YAML, and why does infrastructure love it so much?
So YAML stands for YAML Ain't Markup Language, a recursive acronym which programmers are very fond of.
Of course they are.
It is a human-readable data serialization language. Unlike imperative scripting, where you write commands telling the computer exactly how to do something step by step, YAML allows you to define infrastructure declaratively.
Okay, so you declare the desired end state, and the engine figures out how to achieve it.
Exactly. In the compose file, you simply list the services you desire. You declare, I require a front-end service built from this directory, a back-end service using this specific Docker file, and a database service utilizing the official Mongo image from the internet.
Right.
You define how they network together, which internal ports map to which external ports, and which environment variables they require.
And once that desired state is documented, you replace those 3 massive, complex Docker run commands with one elegant, simple command in the terminal. Docker Compose up the AD.
And that's it. The Docker Compose engine plies the YAML, provisions a secure, isolated virtual network, pulls any missing images, and systematically boots up all the containers in the correct dependency order.
And the AD flag runs them in detach mode, freeing up your terminal for other tasks, right?
Correct.
Now, the source material implements a highly sophisticated architecture here using file inheritance. We have our local development environment and our production Hostinger environment.
Yeah.
Obviously, the configurations differ slightly, right?
Yes, quite a bit.
In development, we want hot reloading.
Right.
In production, we want optimized static serving. But writing 2 completely separate massive compose files violates a core tenet of programming, DRY. Don't repeat yourself.
Absolutely. Duplicating configuration files is a recipe for drift and bugs.
Right.
I mean, if you update a database password in the dev file but forget to update the prod file, the deployment breaks. To solve this, the instructor utilizes compose overrides. They architect a base docker-compose.dml file that contains the core architecture shared across all environments, for instance, the baseline definition of the MongoDB service.
Then they create specialized override files, docker-compose.d.aml and docker-compose.prod.aml.
Exactly. When executing the command locally, they instruct Compose to read the base file and then layer the dev.aml file on top of it.
Oh, nice.
Compose merges the 2 files in memory, replacing or adding specific configurations like mapping local volumes for development while leaving the core architecture intact. It is a highly maintainable structure.
Okay, I want to focus on a critical concept defined within that compose file, port mapping. Let's use an analogy here to visualize network routing. I picture the host machine, my laptop, or the Hostinger server at a massive corporate office building.
Okay, I like this.
It has an external public phone number and thousands of internal extensions, which we'll call ports. The Docker container is a new employee who has been assigned a desk deep inside the building.
An isolated network namespace.
Right. This employee, the Go API container, is stubbornly configured to only ever pick up their desk phone if it rings on extension 80. But the general public, out on the internet, cannot directly dial extension 80 inside the building. The building's firewall blocks it.
Correct. The container is shielded from the host's public network interface.
So port mapping in the compose file, which looks like ADR 81.80, is analogous to configuring the corporate switchboard. We're instructing the main automated switchboard. Listen carefully. If an outside caller dials the building's public number and asks for extension 8001, I want you to instantly, silently route that electrical signal down the internal wires directly to the employee's desk phone on extension 80.
That is an excellent visualization of network address translation, or NAT, which Docker handles under the hood. The first number in the configuration, 8001, binds to the host machine's public interface. The second number, 80, is the target port inside the isolated container network.
And this solves port conflicts entirely, right? I can have 5 different web server containers all running simultaneously, and all 5 of them can stubbornly believe they are running on port 80 internally.
Yeah.
As long as I map them to different external ports on the switchboard, 80way1, 8082, 8083,
Well,
traffic runs perfectly.
Exactly.
Now, as elegant as this orchestration is, the source material forces us to confront a severe architectural vulnerability inherent to containerization: persistence.
Ah, yes. The data problem.
We have praised containers for being pristine, isolated environments, but that isolation creates a massive problem for data. Containers are designed to be ephemeral.
Right. Ephemeral, meaning transient or short-lived. In modern infrastructure, we treat containers like cattle, not pets.
Cattle, not pets. I love that.
It's a common DevOps phrase. You do not nurse a sick container back to health. You terminate it and spin up a fresh replica from the immutable image. The container's internal file system is tied directly to its lifecycle.
Which is perfectly fine for the React front end or the Go back end. They don't store data. They just process logic. If a server container crashes, the orchestrator destroys it, boosts a new one, and the application continues. But Magic Stream has a MongoDB database container.
And herein lies the fundamental conflict.
A user signs up for Magic Stream, they create a profile, they curate a list of their favorite movies, the OpenAI engine generates recommendations, and all that data is written to the database. If that database engine is running inside an ephemeral container, and we terminate that container to push a version update to the network, doesn't the internal file system vanish?
It does.
Doesn't the user data get instantly vaporized into the digital ether?
It absolutely does. If you rely on the container's union file system, deleting the container inherently deletes all data written during its runtime.
That's terrifying.
It is. For a long time, running stateful applications like databases inside containers was considered highly risky for this exact reason. The solution that makes it viable is Docker volumes.
Okay, let's unpack the mechanics of a volume, because this is the lifeline that saves our user data from oblivion.
A Docker volume is a mechanism that intentionally breaks the isolation of the container's file system in a highly controlled manner.
How so?
It mounts a specified directory from your persistent host machine, the actual hard drive of the hosting your VPS, directly into the file path of the container.
So we configure the MongoDB container to operate normally. It believes it is writing its database files to its own isolated internal folder, typically data.d.
Precise.
When the database engine executes a write operation to data.d, the Docker daemon intercepts it. It bypasses the container's ephemeral storage layer entirely and writes the data directly to the persistent folder on the host machine.
Oh, wow. So the data lives outside the container, even though the database process is running inside.
You got it.
This means we can completely annihilate the MongoDB container. We can wipe it from memory. When we deploy an update, Docker Compose spins up a brand new, empty MongoDB container. But crucially, Compose reconnects that new container to the exact same volume portal.
Right.
The new database engine boots up, scans the data.b folder, and instantly discovers the entire data set sitting there waiting for it. The application resumes exactly where the old container left off, with zero data loss. It separates the compute lifecycle from the storage lifecycle, which is absolutely essential for resilient architecture.
Speaking of the database, the instructor includes a fantastic quality of life feature in the Compose setup, an automated seeding script, CJS. Because booting up a massive movie streaming application for local testing is incredibly tedious if the database is entirely empty. You have no data to test the UI against.
Yeah, manually creating test users and inputting mock data is a massive waste of developer time. The Compose file addresses this by configuring a one-off task. When the network initializes, it executes the CJS script against the fresh database.
So it automatically hydrates the database, it creates fictional accounts like our test user Bob Jones, and populates the movie catalog with real titles: The Shawshank Redemption, The Hangover, Once Upon a Time in Hollywood.
It instantly provides a fully functioning, rich application state right out of the box, ensuring that every developer on the team is testing against the exact same baseline data. It's a small detail, but it speaks to professional engineering practices.
And professional developer experience is a recurring theme here, culminating in the utilization of Compose Watch mode.
Oh, watch mode is fantastic.
Docker Compose Watch. This feature seems to resolve the final major complaint developers have about containerization. Historically, if I containerized my app for local development, the feedback loop was excruciatingly slow.
How slow?
If I opened my code editor, found an H2 HTML tag that said Magic Stream, and changed it to Magic Stream my awesome heading, I couldn't just refresh my browser, could I?
No, because the source code inside the running container is a static copy taken at the time of the image build.
Right.
To see your CSS or HTML change, you would have to stop the container, execute a new Docker build command to bake the new code into a new image, and then start a new container, a process taking minutes just to check a typo.
But watch mode changes the paradigm. I noticed in the docker-compose.devi.iml file, the instructor defines specific directories to monitor. If I understand the mechanics correctly, when I save that file in my editor, Docker is actively monitoring my local file system. It detects the file modification, and instead of rebuilding the entire image, it injects that changed file directly across the boundary into the running container, replacing the old file in memory instantly.
It synchronizes the file systems in real time. The front-end development server running inside the container detects the injected file change and instantly hot reloads the browser module.
That's amazing.
You achieve the stability and parity of containerized infrastructure without sacrificing the instantaneous sub-second feedback loop of traditional local development. It is a monumental leap forward in tooling.
Okay, let's take stock. We have conquered the local environment. We circumvented the Vite static build quirk. We orchestrated a complex multi-tier network with Docker Compose. We mapped our network ports via the switchboard. We persisted our critical data with volumes. And we optimized our developer experience with watch mode.
A lot of ground covered.
The application is bulletproof. It is still just running on localhost. It's completely inaccessible to the world. We have to bridge the gap to the cloud. We have to get this architecture onto the hosting your VPS.
Right. And you cannot simply drag and drop gigabytes of container images over a standard SSH connection efficiently. We require a centralized distribution mechanism, a middleman. We need a container registry.
And the source material utilizes Docker Hub. Docker Hub is essentially the GitHub of compiled infrastructure, right?
Yeah.
It is a massive cloud repository where you can upload, version, and store your master molds.
Exactly. But before we upload, the instructor implements a critical environment shift. We stop using the development Docker files and switch to dockerfile.prod to build production-grade images.
Okay.
There is a fundamental architectural change in the React client's production file that we must highlight here. It completely discards the Vite development server.
I saw that. Instead, it utilizes Nginx to serve the application on port 80. Why is this necessary? If the Vite dev server works so perfectly on my laptop, why not just run it on the Hostinger server?
Well, tools like Vite's dev server or Webpack dev server are explicitly engineered for local debugging. They prioritize features like hot module replacement and expansive error logging. They're entirely unequipped to handle the rigors of the public internet.
So they'd crash under load.
Oh, immediately. They lack the optimization to efficiently serve thousands of concurrent connections. They are vulnerable to denial of service attacks, and they're inherently insecure. Nginx, on the other hand, is a battle-tested, high-performance reverse proxy and web server.
Okay.
It is engineered in C to handle massive concurrency with minimal memory footprint. The production Docker file instructs the engine to build the static HTML and JavaScript assets, and then physically hands those raw files over to Nginx to serve to the world securely.
Makes sense. So we build these hardened production images locally, we tag them with a version number, and we execute the Docker push command. For instance, Docker push Gavin LaMagic's stream webprod.1.0.1. The Docker daemon authenticates with the cloud registry, analyzes the layers of the image, and streams the compiled binary data up to Docker Hub. The master molds are now floating securely in the cloud.
They're ready to go.
The next phase is preparing the landing zone. We have to configure the Hostinger server.
And this involves manual server administration. The developer must utilize SSH Secure Shell to authenticate into the remote Ubuntu terminal.
Let's define SSH briefly for anyone who hasn't used it. It's the cryptographic network protocol that gives you a secure, encrypted command line interface into a remote machine over an unsecured network, like the internet.
Yeah.
You log in, and you are staring at a blinking cursor on a server sitting in a data center halfway across the country.
Exactly. From that terminal, the instructor executes standard Linux commands to prepare the environment. They create a directory structure using Impinidir. They clone the project's GitHub repository to pull down the docker-compose.prod.aml configuration files, and they utilize a terminal text editor, like Nano, to manually author the .env file containing the production secrets.
And crucially, they update the API-hosted variable. It can no longer be localhost. It must reflect the actual public IP address of the Hostinger VPS, so the internet routing protocols know where to direct the front-end traffic.
Right.
Now, While they're manually configuring this server, the expert in the source makes a very deliberate, highly specific downgrade to the codebase. And I find this fascinating because it highlights the fundamental tension between technical education and enterprise deployment.
That's a big one.
They intentionally alter the Go backend code to change the authentication cookies from requiring HTTPS secure, encrypted HTTP back to utilizing regular, unencrypted HTTP.
It is a critical pedagogical decision that really requires contextualization.
Totally.
In a real-world production environment, transmitting sensitive authentication cookies over unencrypted HTTP is a catastrophic security vulnerability. Without transport layer security TLS or SSL, the data travels across the internet in plain text.
Anyone can see it.
Exactly. Any malicious actor positioned on a network node between the user and the server can intercept the packets, steal the session cookie, and completely hijack the user's account without even needing a password. It leaves the application totally defenseless against man-in-the-middle attacks.
So if it is that dangerous, why on earth would an expert instructor intentionally break the security architecture of the application?
To avoid completely overwhelming the cognitive load of the student, implementing HTTPS in a containerized environment is not trivial.
It's a pain.
It requires integrating a reverse proxy, like an advanced Jinx configuration or Traffic. It involves proving domain ownership, interacting with certificate authorities like Let's Encrypt, managing cryptographic handshakes, and writing scripts to automate certificate renewals before they expire.
Which is a whole separate course in itself.
Exactly.
Right.
While absolutely mandatory for production, injecting that massive layer of complexity into a tutorial that is already saturated with Docker context, Compose networking, and CI/CD pipelines, it would paralyze a learner.
The instructor explicitly acknowledges this compromise too. I think it's a vital reminder for anyone learning tech. A tutorial is a foundational blueprint. It is designed to isolate and teach specific concepts. It's rarely the fully armored, security-hardened fortress required for enterprise deployment. You have to understand the shortcuts being taken for the sake of clarity.
It is exactly why you don't teach a teenager how to drive by putting them in a Formula One car during a monsoon. You start in an empty parking lot.
That's a great analogy. Okay, so the server's prepared. We manually push the images to Docker Hub. We manually SSH'd into the server. We manually clone the repository. We manually author the environment file.
That's a lot of manual work.
If I want to execute an update, I have to run Docker Compose poll to download the images and Docker Compose up to restart the system. I am exhausted just articulating the sequence.
It's brutal.
The thought of executing this multi-step manual process every single time I find a typo on the homepage, it's miserable. It is brittle, it relies on human memory, and is prone to catastrophic error.
It is the antithesis of modern software engineering. Manual deployments are the primary reason organizations fear release days. Which leads us, finally, to the ultimate architectural solution of this deep dive.
The magic trick. We are building the continuous integration and continuous deployment pipeline using GitHub Actions. The holy grail of DevOps.
A holy grail.
The objective is singular here. From this point forward, the developer only ever types one command on their laptop git push. The pipeline assumes control, and the light hosting your website updates automatically. No manual server logins, no manual pulling, pure orchestrated automation.
Yes.
Let's trace the lineage of CI/CD. Why was this methodology invented in the first place?
Historically, software development suffered from what we called integration hell.
Integration hell, right?
Massive teams of developers would write code in isolation for months. And on release day, they would attempt to merge all those isolated changes together simultaneously. It invariably resulted in massive architectural conflicts, broken builds, and literally weeks of debugging just to get the application to compile.
I can't even imagine the stress.
It was awful. Continuous integration mandates a completely different cadence. Developers merge small, incremental changes into a central repository, frequently, often multiple times a day. Automated servers instantly build the application and run test suites against every single commit, catching bugs within minutes rather than months.
It provides a continuous, provable baseline of stability.
Exactly. Continuous deployment is the aggressive extension of that philosophy. It posits that if the automated test suite passes and the application builds successfully, the code is definitively ready for users.
No human gatekeeper.
None. The pipeline automatically packages the code and deploys it to the production servers without requiring human approval or intervention. You write the feature, you push the code, the users experience it.
The engine powering our specific pipeline here is GitHub Actions. The implementation begins by authoring a declarative YAML file directly in the repository. .github workflowsdeploy.eml. The specific directory path is non-negotiable. Correct.
Yes. GitHub's infrastructure actively monitors that exact .github workflows path. When it detects a valid YAML file there, it parses the declarative instructions to determine the trigger conditions, for example. Execute this workflow only when code is pushed to the main branch, and the sequential steps to execute.
So let's map out the workflow sequence. We push an update to the main branch. GitHub's infrastructure detects it and provisions an Ubuntu runner. What exactly is a runner in this context?
A runner is an ephemeral virtual machine hosted in GitHub's server farms. When your workflow triggers, GitHub dynamically provisions a fresh, pristine Ubuntu Linux server specifically for your job.
So it spins up a computer just for you.
Exactly. It is a completely blank slate, endowed with compute resources ready to execute your defined commands. When the workflow completes, the VM is instantly destroyed.
The runner wakes up and begins executing our script. Step 1. It utilizes an action to check out our repository code, pulling the files into its temporary file system.
Yeah.
Step 2, it executes the Docker build commands, utilizing our updated source code to manufacture fresh, tagged images. Step 3, it authenticates into our Docker Hub account and pushes those new images to the cloud registry.
Right.
Step 4, it establishes an SSH connection into our live hosting or VPS, executes the Docker compose pull command to download the newly minted images, and restarts the containers.
The sequence is highly logical, mimicking the manual steps precisely. However, there is a massive structural security roadblock that must be addressed to make automation possible.
The secrets?
The secrets.
GitHub is a third-party service. It cannot magically bypass authentication to log into your personal Docker Hub account. And it absolutely cannot magically bypass security firewalls to execute terminal commands as the root user on your hosting or server.
No, it can't.
We have to grant the runner permission. We have to provide it with keys. But if we hard code those keys into the deploy.iml file, they are committed to version control and exposed to the public or anyone with repository access.
Which necessitates the use of a secure credential manager, specifically GitHub Secrets. This is a highly encrypted storage vault attached directly to the repository settings. You can store sensitive key value pairs there.
Okay.
During the workflow execution, the runner requests the values, decrypts them in memory, injects them into the terminal commands, and aggressively redacts them from any visible execution logs. Once a secret is saved, not even the repository owner can view the raw value again.
Wow, so it's completely locked down. We populate the vault with several necessary credentials. We store the Docker Hub token and username, authorizing the runner to push images. We store the hosting or VPS public IP address, the administrative username, which is root, and the specific directory path where the application resides. But the most complex and critical secret we must configure is the SSH key. The source material embarks on a deep dive into generating an ED25519 cryptographic key pair using the Shishkage utility. We really need to unpack the mechanics of this because asymmetric cryptography is the absolute bedrock of secure infrastructure automation.
It really is.
If the goal is logging in automatically, why can't we just store the hosting your password in GitHub Secrets and have the runner type it in?
Well, utilizing static passwords for automated script authentication is universally recognized as a severe security anti-pattern.
Anti-pattern, meaning a really bad idea.
A really bad idea. Passwords can be intercepted via keyloggers or man-in-the-middle attacks. They are vulnerable to brute force dictionary attacks. Furthermore, if an employee leaves the company or a script is compromised, you must manually rotate the password on every single server and update every single script that relies on it.
That sounds like a nightmare.
It is. Asymmetric cryptography provides a vastly superior mathematically provable authentication mechanism that requires no shared secrets transmitted over the network.
Let's break down the underlying mathematics conceptually.
Okay, so when you execute Stolzkijin, the algorithm in this case, utilizing elliptic curve cryptography, generates two cryptographically linked files, a public key and a private key.
Public and private.
Right. You can visualize the public key as a highly complex physical padlock. This padlock is not a secret. You can make infinite copies of it. You can publish it on the internet. You can bolt it onto any server door you wish.
So anyone can have the padlock.
Yes. The private key, however, is the exact corresponding physical key engineered specifically to open that one padlock. It is a massive, mathematically unguessable string of characters. You guard the private key fiercely. It never leaves your possession.
The setup process reflects this perfectly then. We take the public key, the padlock, and we transfer it to our hosting or server. Specifically, we append the key string into a hidden configuration file located at Authorized Keys. We are essentially bolting the padlock onto the server's front door and configuring the SSH daemon to say, hey, if any entity attempts to log in and can mathematically prove they possess the private key capable of unlocking this specific padlock, grant them immediate administrative access without prompting for a password.
That's exactly how it works. And to ensure the integrity of that lock, the source emphasizes a strict Unix permission command, chmod 600.
I saw that. What exactly does chmod 600 do to the file?
Chmod modifies the read, write, and execute permissions of a file in the Linux file system. The numeric value 600 specifically dictates that only the absolute owner of the file, the root user, is allowed to read or write to it. All other system users, groups, or external processes are explicitly denied any access.
Okay.
The SSH daemon is highly paranoid by design. If it inspects the authorized keys file and detects that the permissions are too lax, for instance, if any user on the system could theoretically read the file, it will assume the padlock has been tampered with and will outright refuse to accept the keys terminating the connection.
Security architecture is utterly unforgiving. So the padlock is securely bolted to the Hostinger server. We then take the private key, the master key, to open the lock, and we carefully store it inside the encrypted GitHub secrets vault.
Right.
Now the automation is primed. When the GitHub runner reaches the deployment step in the script, it attempts an SSH connection to the Hostinger IP. The server presents a cryptographic challenge. The runner utilizes the private key from the vault to solve the challenge, proving it holds the key without ever actually sending the key over the internet.
The server verifies the math, matches the padlock, the door swings open, and the runner is granted full terminal access. Pure, frictionless automation, completely devoid of password.
Incredible. Once authenticated and inside the server directory, the runner executes the final critical orchestration commands. It issues docker compose pull. Because the server already possesses the declarative docker-compose.prod.aml file, the Docker engine parses it, communicates with Docker Hub, and pulls down the absolute newest layers of the master molds that the runner just pushed moments ago.
It downloads the fresh updates.
And then we arrive at the climax of the entire CI/CD pipeline. The final command executed on the server. Docker, compose and by, remove orphans.
It is the command that orchestrates the entire deployment ballet.
Let's examine the mechanics of this specific execution. If the server is actively serving live users and this command fires, what happens? Does it crash the server, delete the old containers, and leave users staring at a broken web page while the new ones boot up?
No, and that is the brilliance of the orchestration engine. When Compose executes this command, it compares the desired state declared in the YAML file against the current running state. It detects that the underlying images have been updated.
Right.
It initiates a seamless rolling transition. It begins spinning up the new updated containers in the background, fully isolated from live traffic.
It builds a new factory while the old one is still operating.
Exactly. It waits until those new containers report a healthy, ready state. Once verified, the Compose networking layer dynamically reroutes the internal switchboard traffic, pointing incoming requests to the newly minted containers, and gracefully sends a termination signal to the obsolete containers.
Zero downtime. And what about the remove orphans flag?
The remove orphans flag acts as a critical cleanup mechanism. If a previous configuration defined a container that is no longer present in the updated YAML, Compose aggressively terminates and deletes it. This prevents the server from slowly accumulating zombie containers that consume RAM and disk space, eventually crashing the host.
The entire operation accomplishes a deployment with virtually zero downtime perceived by the end user.
It's seamless.
The ultimate payoff demonstrated in the source material is just deeply satisfying to analyze. The instructor returns to their local laptop environment. They open their code editor and navigate to a simple React component. They locate an H2 HTML tag that reads Magic Stream heading. They edit the text to Magic Stream My Awesome heading.
A simple typo fix.
They save the file to disk. They open their local terminal, and they type 3 fundamental Git commands: git add bear to stage the change, git commit to package it, and git push to send it to the repository. That is the entirety of their manual effort.
And the automated domino effect begins.
The push event strikes the repository. The GitHub action detects the event and provisions the runner. You can monitor the workflow interface in the browser. You watch as the runner checks out the code, executes the Docker builds, pushes the new layers to the registry, negotiates the cryptographic handshake with the Hostinger server, pulls the updates, and executes the zero downtime swap.
Magic.
A minute or two passes, the workflow indicator turns green, you open a new tab to the live public host to your URL, hit refresh, And there it is. Magic Stream My Awesome Heading is live, deployed globally.
You never opened an FTP client, you never manually built an image, you never logged into a server terminal.
It is the absolute realization of the DevOps promise. It fundamentally alters the psychology of software deployment. In organizations saddled with manual, convoluted processes, deployment is an event shrouded in fear.
Absolute fear. Developers actively avoid deploying.
They hoard features, batching dozens of commits into massive, monolithic, highly risky deployments that require scheduled downtime and rollback plans.
But when deployment is automated, repeatable, and mathematically predictable, that fear evaporates. You can confidently deploy a single typo fix or a massive architectural change with the exact same level of effort a single Git push. It dramatically accelerates the cadence of development.
So let's synthesize this massive architectural journey. We began by confronting the universal developer pain point, the works on my machine excuse, driven by the chaos of environmental drift.
We solved the drift by encapsulating our React client and Go API into isolated Docker images using raw Docker files, stripping away bloated OS layers by utilizing Alpine Linux.
We encountered the Vite static build quirk and engineered a bypass utilizing template files and NV subs to dynamically inject environment variables at runtime, preserving the immutability of our containers.
We orchestrated that complex multi-tier system alongside a MongoDB database utilizing persistent volumes to prevent data vaporization through the declarative syntax of a docker-compose.email file, leveraging inheritance for environment-specific overrides.
We pushed those master molds to a cloud registry, prepared a Linux server using Nginx for production-grade static serving, and finally wired the entire ecosystem together with a GitHub Actions CI/CD pipeline.
We secured the pipeline utilizing asymmetric elliptic curve cryptography, enabling a frictionless, automated workflow that achieves zero downtime deployments.
It was a phenomenal, professional-grade technology stack. Mastering these DevOps principles really requires a paradigm shift. You transition from viewing an application merely as lines of logical code to perceiving it as a living, breathing, distributed system that must be securely packaged, transported, networked, and operated in hostile environments.
It bridges the gap between coding and true engineering.
It really does. But it leaves me with one final, slightly provocative thought to consider. We initiated this deep dive by examining the Hostinger Docker Manager, GI, the easy way. Paste a URL, click a button, and the system abstracts the complexity.
Right.
We then spent the remainder of the discussion meticulously dissecting the hard way. Terminal grammar, YAML syntax, build contexts, static replacement, and cryptographic file permissions.
The real engineering.
Exactly. So, as cloud computing platforms grow increasingly sophisticated, as AI begins generating infrastructure as code, and as GUI abstractions become even more resilient, are we approaching an event horizon where everyday developers truly never need to understand a terminal command or a YAML file again? Or will the inevitable leaky abstractions of software, the Vite edge cases, the persistent volume failures, the complex network routing, ensure that the engineers who possess the deep granular understanding of the raw underlying mechanics will always be the ones who hold the actual power and control over the internet?
It's a great question.
Something to ponder the next time a colleague looks you in the eye and says, "Hey man, it works on my machine." Thanks for joining us on this deep dive. See you next time.